Hey, good morning or good afternoon or whatever time in the world it happens to be where you are. My name's Steve Hicks, N5AC. I'm CTO, VP Engineering at FlexRadio Systems in Austin, Texas. And we make the FlexRadio line of radios. And I'm going to be talking today about software-defined radio as a platform. So here's kind of an agenda for what the talk's going to be about today. I'll talk a little bit about amateur radio interfaces of the past. These would be everything from serial ports and audio interfaces to radios, that sort of thing. Then I'll talk about what the current industry standards are, not just in the amateur radio world, but also in the commercial world, military, signal intelligence, all that kind of stuff. Then I'll talk about how we've adopted standards in the Flex 6000 radio series and what we think the emerging standards are that are going to be important in the future. We'll talk about hardware adaptability and how having a hardware platform that can take on new interfaces and new ideas really helps from a software-defined radio perspective to bring you new features. Then I'll talk about some of the platform capabilities that an SDR can bring you if it's designed right, and I'll give examples of those, and then we'll be moving on to questions and answers. All right, so first of all, let's talk about why you really want an interface to your radio. There's a bunch of different reasons. I've just listed a few of them here. Be able to control your radio by a computer. So there's lots of reasons for this. You might be running a contest and want to log all of your contacts, and by having access to your computer, you can see the radio interface between the computer and the radio will let you see what frequency you're on. If you're using a spotting network, you can click on call signs in the logger and immediately change frequencies on your radio, and you can keep precise timing and logging information of your contest. You can also use it for DX chasing or digital mode software. For example, if you're using the popular WSJT-X series of programs to do digital modes, these will interface directly with your radio to record what frequency you're on. You can even record your contacts in them as if they were a logging program as well. So that's the control piece of the interface. You also have audio interfaces, and these are primarily for digital modes, but not exclusively. So the WSJT-X program I mentioned is a digital interface program, and so it produces on-air samples that get transmitted, and then it receives samples from your radio and demodulates those into text. Well, this is true for most digital programs. That's how they work, but you could also be using a contest logger, press a button in it, and have hit send CQ for you using your voice because you pre-recorded that and stored it in your computer. So all these types of interfaces use an audio interface typically to your radio. Then you also have the capability of remote access. Maybe you want to access your radio from a remote location, you're on vacation and want to use it or something like that. Access interfaces give you the ability to do that. Okay, so let's look at some of the interfaces of the past and what they were used for. From a control standpoint, rig control, the two main ones that I see more often than anything are CAT and CI5. CAT is the most popular and is supported by most radios. It's a text-like interface that goes over a standard RS-232 style serial cable. Each of the radios, though, that uses CAT has slightly different command formats. So if you're using one manufacturer or another of radio, you might have different sets of CAT commands. And the net effect of that is when you go into your program that controls your radio, you may have to tell it what kind of transceiver you have, both brand and model number, in order to make that capability work. Not all radios also use the same voltage level, although TTL levels, 5 volts, is most common. Some radios use other voltage levels for this. Okay, so what could you do with this interface? We mentioned logging and contest logging earlier, so this would let you figure out the exact time that you made a contact, the exact frequency you're on by reading it from your radio. As I mentioned before, if you're doing any sort of spotting, you can click on spots and it will change the frequency of your radio. Digital modes we mentioned before that do modulation and demodulation and control your rig. Satellite tracking is another common one. The interesting thing about satellite tracking is since most of the satellites that amateurs use are not in a geosynchronous orbit, they will move the distance that they are and the speed they are with respect to your antenna over time and produce Doppler. And so the way to track that Doppler is to get a satellite tracking program which can slowly move the frequency of your radio as you're tracking the satellite based on ephemeris data on that satellite. So again, that's something very easy to do with a rig control program, but it's much, much harder to do without one, to sit there and tune the knob and follow the satellite. And some programs that have computer interface also do rotor control and antenna control along with that. So if you have multiple antennas or you have a rotor on your antenna, some contest logging programs, as you click on different call signs, will actually move your rotor or switch your antenna control based on the band that you clicked on or the location of that station you're trying to work. Okay, so what are the benefits of this kind of radio interface over serial? Well, the command formats are fairly easy. They're easy to look at and understand and see what's going on. You can control most radio functions from these. Rarely will the manufacturer allow you to control all the radio functions. There'll be a number of setup functions and other kinds of things that are not configurable this way. And these serial interfaces are widely adopted. They're used by pretty much any program that wants to do interfacing with a radio would support one or more of these. There are some drawbacks to these older interfaces, though. If you need 2 ports to control 2 different receivers in the radio or that sort of thing, it's often not supported as well in radios. If you need multiple computers or applications to control the radio, so let's say you're using the satellite program at the same time you're using a logger, or you're using a DX program at the same time you're using a voice keyer or something like that, it's sometimes more difficult to make all that work together. And so there's solutions that have been created to help with that, such as virtual serial cables and virtual audio cables and those sort of things. But they require, they're complex and require you some time to set those up. You also have to worry about baud rate setting. This is not a huge deal, but you got to check the baud rate in your computer and on your radio and make sure they're the same in the parity settings and all that, like any serial port. As I mentioned before, each radio has a different command set. So sometimes you can find that radios that are new or even old, the command set's not completely supported, and one feature or another might not work exactly like you expect because it wouldn't be as well supported in the particular software that you have. And this is just due to the differences in the programs and the settings in each of the serial command, the CAT commands, that sort of thing. If you don't have a serial port in your computer, which is much more common now, you can use USB to serial cables to do this, but it's kind of one more thing that you have to deal with, and you have to make sure your computer program is happy to talk over a USB cable instead of a serial cable. The CAT commands are different enough from radio to radio that there have been some abstraction layers in software created. HamLab's an example of those. And another important thing about serial cables is it's difficult to expand these and use them across multiple radios and that sort of thing. It gets very complex very quick because you have all these cables running around. All right, let's talk a little bit about audio. Audio is the other thing that you need to get in and out of your radio. And when I say audio, what I mean is baseband audio that's been converted from the RF signal. So let's say you're doing sideband on 14200. If you put your carrier on 14200, typically from 14200 to 14203, that 3 kilohertz would be your sideband signal. That gets converted to 0 to 3 kilohertz as audio and sent either out your radio as audio or over a USB port to a Windows computer or something like that. If you use analog audio, you do have to deal with analog cables and ground loops and all the other kind of stuff. Another drawback of using the audio in a sound card is you're limited to 16 bits. 16 bits gives you 96 dB of dynamic range if you can use all 16 bits, but many modern transceivers actually have a much broader capability than that. So 100, 110 dB is not unusual. And so what the radios have to do in order to use audio is they either have to truncate this, they either lop off the top or the bottom, or they do some sort of companding in order to fit the audio into 16 bits. So as I mentioned, some of the pros here is that the audio format's widely adopted. Pretty much any digital program you run on a computer can access the audio format, even though it's only 16 bits. And then you can have digital modes that can assist with troubleshooting. Okay, so let's talk about some of the cons here of the audio. I mentioned the dynamic range limitation. If you have a radio that has high dynamic range, which many of the radios do today, that has to be converted into a lower dynamic range signal for piping down into audio. So you lose some of your dynamic range that you paid for with your radio in doing this. If you're transporting an analog audio signal around, your fidelity can sometimes suffer, and there's lots of reasons this happens. One might be ground loops, another might be that you've got RF entering your analog cables or things like that. So it's best to ship things around digitally if you can. There is also the level control issue. So if you have a sound card on your computer that's generating a digital signal into your sound card, you're transporting that as audio over to your radio, you've got to set the mic gain on your radio commensurate with whatever that level is coming from your computer. So it's one more thing to set up. And then you have the opposite situation on the other end, where you may have to adjust the quote-unquote volume control on that sound card coming into your digital mode program to ensure that you're not overloading or not providing enough audio for the digital mode program to do what it's designed to do. You can actually reduce even further your 16-bit audio by misadjusting your volume control or your mic gain. Another problem that can occur here is you may have to have some understanding of some signal phenomena such as crest factor to get everything set up correctly. So this would be if you're using a digital mode that uses multiple carriers, you may need to understand exactly how the signal will peak when those multiple carriers all coincide at a positive voltage and create a much larger signal. I mentioned ground loops, and so a common way to get around this if you're piping audio between your computer and your radio is to use what I would call a box of transformers, but it's some kind of signal interface box or something like this where you've built up isolation transformers to prevent having ground loops or anything like that. Okay, so let's move on and talk a little bit about industry standards and what's going on in terms of interfaces in our industry. So RF transceivers, which are also called in our industry sensors or spectrum apertures or something like that, these are the names that they take on in the radio world that's not amateur, and then in the amateur world we often just call them transceivers. So what kind of standards are available? Well, one of them is SDDS, which stands for Signal Data Distribution Service. This was widely used in the past, but it's falling more out of favor. In the favorite one to use now is VITA-49, which is Vita Radio Transport, which allows you to send audio signals or those IF signals, RF signals, any of those things completely digitally from your computer to a transceiver and back and forth. CAT is, of course, a de facto standard, and it's widely used, as well as Windows sound cards, as we mentioned earlier. So let's talk about each of these standards and what they provide. VITA-49 has structures for both control of your transceiver as well as streaming RF-IF data, and it also has the capability of handling FFT or spectrum plots, metering, other kinds of things like that. So it's a pretty all-encompassing standard for data coming to and from a transceiver. SDDS provides just the streaming RF-IF, and I'm not going to spend any more time on it because it's falling more out of favor. CAT is really about control, and Windows sound cards just about the streaming audio RF-IF data. So as you can see, VITA-49 is a pretty all-inclusive standard compared to the others. So at FlexRadio, we initially supported both CAT and Windows sound cards because they're so well supported in the amateur community, and we wanted to allow our customers to do the same kinds of things and use all the software that's available. So we support both these, and we'll continue to support them because they are important in our industry. In 2008, we built our first product, CDRX, followed by SDRX, that uses the VITA-49 interface. These are not amateur products. These are used for other purposes, but we adopted VITA-49 for these. And then in 2010, we built another product that uses both SDDS and VITA-49. So we have over a decade of experience with both of these streaming data interfaces. So in 2012, when we built the first Flex 6000, we made a long-term commitment to VITA-49 because we felt like it was going to be the standard moving forward that continued to be in wide use. And so far, as of this year that's borne out, and it is the standard that continues to grow and be the one that's most robust in and outside the amateur community. As I mentioned, the key thing it does is internal and external. Well, it does streaming of RF and IF data, but we use it for both internal and external streaming. What do I mean by that? So as a user of one of our radios, an operator, you're able to use VITA49 data to get any kind of streaming data in and out of the radio. So everything from microphone audio to on-air digital samples for receive or transmit can all be done using VITA49. But we also use VITA49 inside the radio, and I'll show you a little bit about what that looks like. And it gives us a lot of flexibility in how we do things, and in my opinion is a key thing that differentiates our SDR from others because it uses VITA49 internally. VITA49.0 was the initial standard. The current standard is 49.2, and it does have some facility for command protocols now. As of today, we don't support those, but we're likely to begin supporting those in the future. So this would be a substitute for CAT kind of commands. As I mentioned, VITA49 has been widely adopted, and SDDS is falling out of favor. All right, so let's take a little bit a look at what SmartSDR API looks like when we're using CAT. So if you have your transceiver on the left, we have a library which we call FlexLib that has a C# interface that anybody writing to that can get access to any of the functions inside the radio. And then as you can see on the left over there, we layer SmartSDR CAT on top of that, which provides a CAT interface, which then we connect to a virtual serial driver in Windows. So as a Windows user using any Windows digital application or logging program or anything like that, you have access to CAT, and it looks like it comes through in a virtual serial driver. So you'll see a COM port show up, which looks like a physical COM port connected to the radio, yet all of this flows over a TCP/IP link to the radio through the one Ethernet cable coming out of the radio. So there's no extra cables or baud rates or anything like that to worry about. It's all done over this one cable. So you can see there on top, on the upper left, I have CAT-enabled applications. So this would be any one of your loggers or digital mode programs or anything that uses CAT is able to communicate through the radio in this mechanism. The other thing that we allow on the right-hand side there is a SmartSDR-based application if you want to use our API. The benefits of using our API, the SmartSDR API, is it gives you full access to everything in the radio. And by full, I mean full. So if you look at SmartSDR for Windows, which is our client application that most people use to access the radio, that application uses our API to access the radio. So literally anything you can do in our application, you can do with this interface on your Windows computer. So we've encouraged developers to adopt the SmartSDR API to give them more capability and insight into the radio. And to date, over 150 developers have used that interface. So as a software developer, why would you care about using that interface instead of CAT? What would the reason for that be? Well, if you look at a Flex 6600, for example, it has 4 receivers in it that have a lot of capabilities that go way beyond the definitions that are in CAT. And it would be very complicated to try and expand CAT to explain to it that there's 4 receivers in the radio and they all have different characteristics and those kind of things. And you can move the transmitter between each of those receivers and that sort of stuff. So instead, we created a different API that's used for that purpose, and we encourage developers that want to expand and use that to use it. Okay, DAX is another equivalent interface, but on the sound card side that gives you access to the streaming data. So through the same FlexLib C# library, we provide access to streaming IF data or data from your receivers in the radio. So as you can see on the left, we have a VITA49 to Windows sound card driver. This is called a DAX driver. And then that places that data available through a Windows sound card, and then you can use whatever application you want layered on top of that, which was WSJTX, FLDigi, whatever else that happens to want to use a Windows sound card driver. Now, if you go through this path that I show on the left here, you do go from many more bits, something in the vicinity of 22 bits per receiver, down to 16. So you lose some dynamic range going that way. So we also provide the raw VITA49 interface on the computer as well, and we've encouraged digital mode software engineers that are writing those kind of programs to adopt that interface, because with the VITA-49 interface they get access to the full dynamic range of the radio instead of a smaller companded version of that. If you're on a Mac or Linux or any other kind of computer that doesn't have the C# FlexLab on it, you can access the VITA-49 interface directly from the radio as well. So these are available on all different platforms. We just happen to have a library that uses the C# way of doing things, the calling method for Windows. Okay, so let's take a look here. See if I can get this to give me all the boxes here. Look at VITA-49 being used inside of FlexRadio. So this would be for our current line of radios, which we call Deep Eddy. I show up there in parentheses DE. So this would be a Flex 6400 or Flex 6600, 64M, 66M, this series of radios. So we'll do VITA-49 over UDP here between the radio and the computer. And then to show you what this looks like inside the radio, you can see there's a ADC that's for the receiver, and there's also a DAC. See, here's the DAC that's for the transmitter. So the ADC is an analog to digital converter and is a key piece of the receiver that takes the off-air signals and converts them into parallel data. The DAC does the other end of that and takes the parallel data from our radio and converts it into an RF signal for transmission on the air. So the two of these constitute a receiver and a transmitter inside your radio. The FPGA here, which is a flexible programmable gate array, it's a programmable part that allows you to run all kinds of filtering algorithms, decimation, down conversion, up conversion, all sorts of things like that inside the radio. So that's the key component we use to do that. But then out of the FPGA, we speak VITA-49 through an Ethernet switch to our CPU. And this gives us a lot of flexibility, because today we take data from the, in this example we take that data from the FPGA for our receiver, but that data could also come from a remote radio and be used inside our radio to combine receivers or do all kinds of things like that, because we're using VITA-49 as a common transport across everything that we do. On the right over here you see a computer, and the computer connects in through an Ethernet switch, so it has access to any of this VITA-49 data that comes directly out of the FPGA or out of the CPU as we've post-processed it and demodulated it and that sort of thing. So I don't want to spend a whole bunch of time on this picture, but the key takeaway here is that we use VITA-49 both inside the radio as well as outside the radio. So why do we do that? It is the only streaming IF format that we deal with inside the radio, and one of the key reasons we use this is, since VITA-49's definition is that it's based on UDP-IP, which is a internet protocol that's been around for 30 or 40 years, we can push this data over any Ethernet link. So this allows us to use it internally in the radio through our Ethernet switch, outside the radio through the Ethernet switch or Wi-Fi access port in your house, or send the data clear across the world using SmartLink to connect to your radio remotely. So it gives us a common way to send data around. The radio internally, as well as our clients, don't really care where any of that data comes from as long as it's in the right format. So again, that allows us to put the user receiver locally or remotely, or transmit, receive remotely, locally, use a computer here with your radio somewhere else, whatever else, and we don't care about where any of that stuff is. So this allows us to create and to design and support disparate distributed applications because of this. And there's lots of examples of this. In recent years, we've allowed you to do SmartLink over the radio, which allows you to access your radio remotely, as well as multiflex, which allows more than one person to use your radio at the same time. And these are all capabilities that came about because we had adopted VITA-49 inside and outside the radio. So I think I've talked mostly through this picture already. Probably don't need to talk about that again. The only other thing to show here is that you can have a VITA-49 application outside the radio as well. So what does this buy you? If you want to write your own waveform or digital mode application, you can use VDA49 outside the radio to access the data in the radio and communicate with it. So why do we use VDA49 to go from the radio to our client programs and that sort of thing? Since we're under control of both the radio and our client programs, we don't have to go use a standard. But by using a standard, it allows anybody to connect to our radios and not use our client if they want, to create a new client using standard interfaces, any of those kind of things. And also because everything in our ecosystem, from the insides of our radio to the clients on the outside, use VDA49, we can mix and match and swap any of those pieces and move them around, and everything just works. An example of this is what we call the Waveform API. You may or may not have heard of this, but it's another API in our radio that allows you to add new modulation, demodulation schemes to the radio. And it's been used many times to create new capabilities for the radio. Two that are readily available for amateurs is Codec 2 FreeDV, which is a waveform that you can run inside the radio, and you can run a client outside the radio to control it, which gives you FreeDV access without any other external hardware. Another one is D-Star. Because D-Star uses a proprietary codec, we utilize a device called ThumbDV, which plugs into the USB port of the radio, but then that uses the Waveform API to do D-Star transmit and receive through the radio. So I've talked a little bit about waveforms and what those are and what the benefit can be. So for us, a waveform refers to any external modulation means like, it could be anything, upper sideband, Codec 2, FT8, any of those things are waveforms. And we allow this common waveform interface to run outside the computer or inside the radio, or outside the radio or inside the radio, so that you can add additional waveforms to the radio. So today in the amateur world, there's only been a couple of those that have been adopted, the two that I mentioned, Codec 2 and D-Star. But in the future, as new waveforms are added, because we've in the amateur world, we can go create those for use in the radio very easily because of this interface and the adoption of VDA49 and the APIs that we have. So you can see in the picture here, we show there's a receive and transmit signal chain. These are essentially the things that take, on the receive side, it takes the raw samples from the receiver and then formats those, passes them on to the waveform receiver that does its demodulation. And then on the transmit side, it can do modulation of the waveform, pass it to the transmit signal chain, which can put it on the air. As I mentioned earlier, you can, once you've created a waveform external to the radio and made that work using the interfaces that are available, the same interfaces exist inside the radio, and you can migrate that same waveform for running inside the radio itself. So what's the benefit there? Let's say you've created 4 or 5 new waveforms that you think are really useful in the amateur world. You can develop those on an external computer, debug them, make them all work along with your radio. And then once you have that working, you can target them for development for a production inside the radio and create a package which can be loaded into the radio. And from that point forward, anybody that owns a Flex 6000 radio can download that package and run it inside their radio and have that new waveform. So this is a very unique capability in the amateur world, that somebody can go create a new digital or voice or whatever kind of mode and actually make it work inside your radio. Okay, so I want to shift gears a little bit now and talk about what kind of hardware elements and pieces you need inside a radio to make it an SDR, what I would call a true SDR. So SDR is kind of an overused word, and on one side of the spectrum, anybody that has a microprocessor in a radio might decide to call their radio a software-defined radio because there's software on the processor and that controls the radio. On the other end of the spectrum is a radio that is completely defined by software. All the modulation, demodulation, control, everything is done in software. And a radio like that is almost infinitely programmable. So I want to show you what a radio like that looks like and understand what the pieces are inside. So I know this is a bit of an eye chart, but let's talk about what some of the pieces are. I'm going to start in the upper left here and kind of work my way around clockwise and talk about the different pieces. So the first blue blocks you see in the upper left are preselectors, and these are filters that filter out RF energy by band typically. So these would be your band select filters, and these need to be in hardware. Why do they need to be in hardware? Well, if you have signals that are strong enough to overload your analog to digital converter that are out of band, and you do not have a preselector, then you won't be able to receive with your analog to digital converter because it will be overloaded. So the preselector gives you capability to be near very, very strong signals that your receiver can't normally tolerate and protect you from that. So it's not often that hams are in this situation, but some common situations that occur are if you're near a broadcast station, if you're a multi-op contester where there's multiple radios in the same location, or if you're at field day. Any of those things are likely reasons to have a preselector, and they do need to be actually created in hardware filters made from inductors and capacitors and those kind of components. So from there we go into an analog to digital converter that takes the analog RF signal and turns it into a digital signal. Because we're a direct sampling software-defined radio, that means that we create these huge data streams out of these ADCs. For example, in a Flex 66 or 6700, each one of these ADCs produces 4.3 gigabits of data, which is a lot of data. So we have to go take that data and do down conversion on it to create smaller, less wide bandwidth receivers then that we can do demodulation, filtering, and all those sort of things on. And so this is what the next block over, the FPGA, does. It down converts those receivers. It also does fast Fourier transform, which produces the fancy pan adapter displays and waterfall displays that you see in a modern SDR. And on the transmit side, we also do up conversion, which takes a narrower bandwidth, whether it's 24, 48, 96 kilohertz worth of data, and up converts that to the RF spectrum and then puts it on the air. We'll go ahead and cover these two pieces that do that. There's the digital to analog converter, which does the opposite of the analog to digital converter. It takes the stream of data, converts it into an analog RF signal, which then we put into a power amplifier and a harmonic filter like any radio would. So these 6 blocks that you see, preselector, power amp, DAC, ADC, and all those are purely analog components that you have to have in the radio. The FPGA is a digitally reprogrammable part. Now the data out of the FPGA for us goes to an Ethernet switch, which allows us to have a lot of different things looking at and providing that data. It's a very unique capability. As far as I know, we're the only radio manufacturer that employs an Ethernet switch inside the radio. And then on the right-hand side, we have our baseband processor, and it's responsible for doing all of the filtering. So if you want to change your filter on voice or CW to a different bandwidth, you want to go from 500 hertz to 100 hertz on CW, all that kind of stuff is done in the filtering in the baseband processor. We do the modulation and demodulation, so anything that takes the spectrum and converts it from raw samples into AM, FM, CW, sideband, all those kind of things are done in the baseband processor. Of course, we control the radio. We're responsible for all the internal and external communications to your client that exists outside the radio, any of those kind of things, as well as the visualization aspects of the radio. So this would be all of the visualization of filters and the pan adapter and waterfalls and metering, signal metering, SWR metering, all that kind of stuff's done in the baseband processor. And then in the lower left there, or the center I guess, we show a couple of different clients that can be connected to the radio. And in our case, with a capability like multiplex, you can have more than one operator actually connected to the radio operating it at the same time. So just to highlight here where the real programmable pieces are in the radio, the FPGA and the baseband processor both take lots of software and are reprogrammable. And everything that you see here that's in red is a piece of software that's been written to make this radio work. So you can see that the bulk of what goes on in the radio is all defined by software. All right, so why do we care? Why do you care if you have a software-defined radio and has all these programmable parts in it? Well, I kind of want to step through this table here and show you some of the things that come out of this capability. So one of them is a new modulation mode. If you have a baseband processor as a reprogrammable component, and you have an API, a waveform API that allows you to create those, then you can go add new waveforms to the radio. Examples of those in the Flex 6000 series are Codec 2, FreeDV, D-Star, those kind of things that we've added to the 6000 over time. So somebody who bought a Flex 6700 back in 2012 had no idea we were going to go do that, but then later, because we had these capabilities, the programmable baseband processor, and we created the waveform API, it allowed the addition of these. Another example would be the introduction of new filtering. So as I mentioned, we do most of our filtering in the baseband processor. You can also do it in the FPGA. We're just today doing much of it in the baseband processor because we have the horsepower there. And we have a flexible software architecture to support that. So an example we've done in the Flex 6000 is we added new filter sharpness settings over time that didn't exist when we first came out with the radio. And having that programmable baseband processor allowed us to do that. Another example would be remote capability. So if your baseband processor is connectable to the Ethernet and supports TCP/IP, and that's something that you've embraced in the radio design, and you have VITA-49 and those kind of capabilities, you can do that. And that's exactly what we did when we created SmartLink, which allows you to access your radio from anywhere in the world over the internet. And it really feels like you're sitting right in front of the radio. Multiple operators using the same radio. Again, this is the same kind of thing because we have the programmable baseband processor that's connected to the Ethernet spigot on the radio. We can allow more than one person to connect to the radio and operate the radio at the same time. And because most of our radios have 2 or more receivers in them, each person can have their own receiver and operate in some ways autonomously from the other operator. Wideband noise blanker is another example. It's very common to get noise blankers that work at 24, 36, 48, 96 kilohertz. But to have a really good noise blanker, it helps a lot to have a much wider input of signals into the noise blanker itself. So we have the capability of looking at up to 24 megahertz worth of data at a time in our FPGA. And so this is what we did to create our wideband noise blanker in the Flex 6000. Again, this was created well after many people bought their radios, but because we have the capability and the extra capacity in the parts, we can go add something like this later. Ultra-wideband data output. With DACs, today we support up to 192 kilohertz, but we have the capability of supporting much wider bandwidths, which we're doing for some non-amateur customers today. And again, this is primarily because we have the FPGA that can produce these wider bandwidths, but also because we have an integrated Ethernet switch in the radio that allows us to route that data directly out of the radio. Some wide bandwidth data has so much data in it that it would swamp a baseband processor. So we have the Ethernet switch to help us out and allow us to send that data out of the radio without any kind of issue. Another example would be remote FT8 client. If you wanted to do WSJTX modes like FT8 and you wanted to use that client remotely, you really do need the ability to access the radio, both its control and its streaming data remotely. So an example of that in the Flex 6000 realm is the SmartSDR for iOS iPad app, which allows you to do FT8 on the radio remotely. So this is just an example of what you can get out of some of these capabilities. Here's a filter skirt comparison. The green line is top of the line INRAD analog filter that you might find in many radios for CW, and the blue is the 500 hertz shape factor 1.04 radio filter that's in the Flex 6000 series. So this is something that if you have a true SDR, you're able to program things like this in your radio. Here's some more additional capabilities. Adjustable CW waveforms, so you can adjust the rise and the fall and make a completely perfect looking CW waveform in your radio with the right baseband and processor or FPGA. Full duplex is another capability that's very unique to the Flex 6000 series, and we're able to do that because we have the baseband processor and FPGA as well as a completely separate receiver and transmit chain, so we can operate the receiver and the transmitter at the same time in different frequencies. That fundamental capability also allows us to do SO2R in one radio. So before, if you want to do single operator 2 radio capability for contesting, you had to own 2 radios. And with this technology, you can do this in one radio. Again, this is enabled because we have these capabilities and we have full duplex inside the radio. Another example of a capability you could add would be a new speech processor. We put ours in our baseband processor because we had the performance to do that and because it was reprogrammable, and we integrated the CESSB speech processor, which was written up in QEX, and actually the research to create that speech processor was done on our hardware. Another thing that we've added because of these capabilities is the integrated pan adapter spots. So you can now pull spots in from an external spot source and show them directly on the screen of your radio or in a remote client. And again, this is because the baseband processor is programmable, connected to the internet, and we're able to grab that data and then show it in your radio. So this is an example of creating a virtually perfect CW waveform by having this reprogrammable capability in the radio. This is just a standard CW looking waveform here that we've created. Here's the CESSB speech processor that we added to the radio. Again, you could have bought a radio in 2012 without this capability, and then we added it in 2014 or 2015. I can't remember which one. And it's a really great speech processor that gives you about a 2.5 dB power improvement with excellent speech intelligibility. Here's an example of doing spots in the spectrum. This is actually the FlexRadio iPad app, and you can see the spots back there showing where FT8 signals are. Here's an example of the FT8 tool running on the iPad and a contact being worked here.